Greetings of the day to all of you. In our previous lecture, we had discussed a three-phase unbalanced system. This lecture is a continuation of previous lecture. So I will write here three-phase unbalanced system. And in that three-phase unbalanced system, we are considering case 1. The case is that both voltages and currents are unbalanced. Both voltages and currents are unbalanced. This is the case. And if you remember, we got a mathematical expression for instantaneous power, three-phase power, which was PA bar plus PB bar plus PC bar. That is the constant terms, average power of phase A, average power delivered by phase B plus average power delivered by phase C, and then oscillating components of the active power, PA oscillating plus PB oscillating plus PC oscillating. And we found that the power is VAIA cos phi A, which is delivered to the load, VAIA cos phi A plus VBIB cos phi B, VBIB cos phi B plus VCIC cos phi C. This is PA plus PB plus PC. Plus then there was a relation for PA plus PB plus PC oscillating components of the active power, which I am not going to write here. And we found that this PA oscillating plus PB oscillating plus PC oscillating, this term is not equal to 0. Meaning that in addition to average power which is delivered to the load, actually your power is not constant like a three-phase balanced system. For a three-phase balanced system, your power, instantaneous power, is constant, 3VI cos phi. But here instantaneous power is not constant. It comprises of these average terms and oscillating terms. It may be oscillating something like this. So therefore, whenever there are unbalances in voltages and currents in a three-phase system, we lose the advantage of a three-phase system over a single-phase system. What was the advantage of a three-phase system over a single-phase system? That instantaneous power delivered by a three-phase system is absolutely constant, given by 3VI cos phi. But as soon as your system becomes unbalanced, that advantage is lost. Instantaneous power delivered by source to the load, it becomes oscillating. Now let us derive the mathematical expression for instantaneous reactive power. I will write here instantaneous reactive power. We already have the relation for instantaneous reactive power using H. Akagi's research, where he used ABC to alpha beta O transformation and gave us this relationship for instantaneous reactive power in a three-phase system. That is, instantaneous reactive power Q of T is equal to minus 1 by root 3 times VBC into IA plus VCA into IB plus VAB into IC. We can write this QT like this also. It's minus 1 by root 3 times VBC. We can write as VB minus VC, because what is line voltage VBC? It is the phasor difference of phase voltages VB and VC. So it is VB minus VC into IA plus VC minus VA into IB plus VA minus VB into IC. Now we have the relations for all these quantities. So we can write instantaneous reactive power equal to, or let me write that here. Instantaneous reactive power Q of T will be equal to minus 1 by root 3 times, what is VB? VB is root 2 VB sine of omega T minus 120 degrees minus 5 VB, okay, minus VC. VC is root 2 VC sine of omega T plus 120 omega T plus 120 degrees plus minus 5 VC. Okay, this whole bracket closed multiplied by IA. What is the mathematical expression for IA? We know IA is root 2 IA sine of omega t minus phi IA. Okay, so that completes this term VB minus VC into IA. This is VB, instantaneous phase voltage VB, minus instantaneous phase voltage VC. This whole thing multiplied by this current. Okay, so we can put it within the curly brackets, minus or rather plus VC minus VA into IB. What is VC? VC is root 2 VC sine of omega t plus 120 degrees minus 5 VC. Okay, minus VA. VA is root 2 VA sine of omega t minus 5 VA. Okay, into into IB. IB is root 2 IB sine of omega t minus 120 degrees minus 5 IB. Okay, so this is second. Now third term is VA minus VB into IC. Now plus VA is root 2 VA sine of omega t minus 5 VA. Okay, minus VB minus root 2 VB sine of omega t minus 120 degrees minus 5 VB into what? This curly bracket should be here. Similarly, this curly bracket should be here. Into IC. We have IC here. What is the mathematical expression for current IC? It is root 2 IC sine of omega t plus 120 degrees minus 5 IC. That's it. So now therefore Q of t will be equal to minus 1 by root 3 times. Now you have this equation for voltage multiplied by current. So this into this, that is root 2 VB sine of omega t minus 120 degrees minus 5 VB into current. What is current? Current is this, root 2 IA sine of omega t minus 5 IA. So that is this term multiplied by current. Then minus this term into current. So minus, what is the second term? Root 2 VC sine of omega t plus 120 degrees minus 5 VC into current. And what is current? Current is root 2 IA sine of omega t minus 5 IA. So that is this into current minus this into current, plus then this into current IB, VC into IB, then minus VA into IB. So plus, I am writing next term plus root 2 VC into sine of omega t plus 120 degrees minus 5 VC into this current IB, which is root 2 IB into sine of omega t minus 120 degrees minus 5 IB. Okay, minus this into current, this term, it is minus root 2 VA sine of omega t minus 5 VA into current IB, that is root 2 IB sine of omega t minus 120 degrees minus 5 IB. Okay, then plus this voltage, instantaneous voltage VA into instantaneous current IC, minus instantaneous voltage VB into instantaneous current IC. So I don't have space here, so I will have to carry it on to top of the table, that is here. So it is in continuation with this. I will take this arrow here. in continuation with this, plus root 2 VA sine of where are we? Yeah, root 2 VA sine of omega t minus phi VA into current IC, which is root 2 IC sine of omega t plus 120 degrees minus phi IC. Then minus this into this, VB into IC, that is minus root 2 VB sine of omega t minus 120 degrees minus phi VB into IC. IC is root 2 IC sine of omega t plus 120 degrees minus phi IC. Fine. So this is the equation after simplification, after multiplying various terms. Now let me rub off this portion also. So therefore QT, instantaneous reactive power, will be equal to minus 1 by root 3 minus 1 by root 3 times what is inside is, see, this is root 2 into root 2. Root 2 into root 2 is 2. Then VB into IA. Let me first of all write product of RMS value of phase B voltage VB and RMS value of phase line current IA. So VB into IA. Then root 2 into root 2 is 2. 2 sine of omega t minus 120 degrees minus phi VB into sine of this, sine of omega t minus phi IA. Okay, so this is first term. Then minus, now product of this and this. This is VC, this is IA. VC into IA is VC IA. And then root 2 into root 2 is 2 sine of omega t plus 120 degrees minus phi VC, omega t plus 120 degrees minus phi VC into sine of omega t minus phi IA. So these are these two terms. Okay, this into this minus this into this, then plus this into this, plus, now this is VC, this is IB, so VC into IB, then multiplied by root 2 into root 2 is 2 sine of omega t plus 120 degrees minus phi VC, we are here, into sine of omega t minus 120 degrees minus phi IB. Let me check it. VCIB. Yeah, phi IB. Yes. Plus VC, 2 VCIB, phi VC, phi IB. Yeah. Then we have this term. This into this we have done. Then this into this. Now this is minus VA into IB. That is VA IB. Then root 2 into root 2 is 2 sine of omega t minus phi VA, that is this, into sine of omega t minus 120 degrees minus phi IB. Fine. So then we have other two terms which I had written just few moments back on the top of it. I don't have those, but I have already written those on the piece of paper. So you can continue like this. So how many terms I have got? 1, 2, 3, 4. I should get 2 more terms. This. First term, second term, third term, fourth term. Now I plus next term, if you multiply those two quantities, this is VA into IC into 2 sine of omega t minus phi VA into sine of omega t plus 120 degrees minus phi IC. And last term is minus VB IC 2 sine of omega t minus 120 degrees minus 5EB into sine of omega t plus 120 degrees minus 5IC. That's it. Now let me close the bracket. Minus 1 by root 3 times all this. How did we get it? By multiplying the consecutive terms. Now this is VBIA 2 sine A sine B. Similarly, minus VCIA into 2 sine A sine B. Everywhere you will find the identity 2 sine A sine B. And using the identity 2 sine A sine B, 2 sine A sine B equal to cos of A minus B minus cos of A plus B. If you use this identity, let us see what we get. So therefore, instantaneous reactive power will be equal to minus 1 by root 3 VBIA. This is 2 sine A sine B, which is cos of A minus B. What is A? A is this, omega t minus 120 degrees minus 5EB minus B. B is this, omega t plus 5IA minus cos of A plus B minus cos of A. A is omega t minus 120 degrees minus 5EB plus B. B is omega t minus 5IA. Okay. So this is what we get from first term. VB into IA, 2 sine A sine B is cos of A minus B minus cos of A plus B. Similarly, we can do it for second term, then third term, then fourth term, fifth term, sixth term. Doing like this, we will get other terms. When you will derive this expression, you will have everything in front of you, but unfortunately here I have to rub off because I have a small board. I don't have a large board. I cannot retain these equations, but I have these equations. I have already done this exercise. I have derived these equations on the piece of paper here. So I will keep this piece of paper here and I will show you the other terms. So first was VBIA cos of this, and then minus this cos of this. Next is minus VCIA times cos of omega t plus 120 degrees minus 5EC minus omega t minus 5IA minus cos of A plus B, that is omega t plus 120 degrees minus 5VC plus omega t minus 5IA. Okay. Then I don't have space here, I have to go here, plus VCIB times cos of omega t plus 120 degrees minus 5EC minus omega t plus 120 degrees plus 5IB, okay, minus cos of omega t plus 120 degrees minus 5EC plus omega t minus 120 degrees minus 5IB. Okay. The next two terms are minus VAIB times cos of omega t minus 5EA minus omega t plus 120 degrees plus 5IB minus cos of omega t minus 5EA plus omega t minus 120 degrees minus 5IB. Closed. And then I have next two terms plus VAIC times, what is inside is cos of omega t minus 5EA minus omega t minus 120 degrees plus 5IC minus cos of omega t minus 5EA plus omega t plus 120 degrees minus 5IC. Bracket closed. And finally I have last two terms, minus VBIC times cos of omega t minus 120 degrees minus 5EB minus omega t minus 120 degrees plus 5IC minus cos of omega t minus 120 degrees minus 5IB phi VB plus omega t plus 120 degrees minus phi IC. That's it. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms. Now go to first term. In this first term, omega t plus omega t minus omega t goes. Okay. So what you will get is after simplification, cancellation of terms and simplification, you will get instantaneous reactive power equal to minus 1 by root 3 times. First you will get VBIA into what is inside, omega t and omega t goes. So you will get phi cos of phi IA minus 120 degrees minus phi VB, and minus omega t plus omega t is 2 omega t cos of 2 omega t minus 120 degrees minus phi IA minus phi VB minus phi IA minus phi VB. Fine. So this is first term. Then minus VCIA cos of, in this VCIA also omega t plus and omega t minus goes. So you will get cos of phi IA it is here plus phi IA plus 120 degrees minus this phi VC minus cos of omega t plus omega t is 2 omega t plus 120 degrees, because 120 degrees is there, minus phi IA minus phi VC minus phi IA minus phi VC. Okay, I don't have other terms. I have already rubbed them off, but I have already done this job here on this piece of paper. So I will write the other terms, which you can very easily write while deriving this equation. Plus VCIB times cos of phi IB plus 240 degrees minus phi VC minus cos of 2 omega t minus phi IB minus phi VC. Okay. Next is minus VAIB times cos of phi IB plus 120 degrees minus phi VA minus cos of 2 omega t minus 120 degrees minus phi IB minus phi VA. The next is plus VAIC times cos of phi IC minus 120 degrees minus phi VA minus cos of 2 omega t plus 120 degrees minus phi IC minus phi VA. And finally, last term is minus VBIC. Last two terms within the bracket are cos of phi IC minus 240 degrees minus phi VB minus cos of 2 omega t plus phi IC minus phi VB. That's all. This is the instantaneous power. Now, interestingly, you can see just like active power, the instantaneous power has these terms, cos of this and cos of 2 omega t minus something. Similarly, here in the second term, VCIA times cos of some angle inside minus cos of 2 omega t plus or minus some angle inside on all the terms. That means your instantaneous reactive power also has an average value, which is given by these terms, 1, 2, these cos terms. VBIA cos of phi IA minus 120 degrees minus phi VB plus cos of phi IA plus 120 degrees minus phi VC plus this plus this plus this plus this, and it has oscillating terms like this, minus cos of 2 omega t minus 120 degrees minus phi IA minus phi VB, then minus cos of 2 omega t plus 120 degrees minus phi IA minus phi VC minus this minus this minus this minus. Why these are oscillating terms? Because these are all oscillating terms they are oscillating at 2 times the supply frequency, 2 omega. Omega is the supply frequency. So therefore, if you have to find the average power, okay, average power will be minus 1 by root 3 times this term plus this term plus this term plus this term plus this. What you have to do, average power, how you can find average reactive power? Average power you can find by integrating this whole term in 1 by t integration 0 to t qt dt. When you integrate all these terms, this cos 2 omega t terms will become 0. You will be left with these terms only. So therefore, average reactive power will be like this. Therefore, Q will be equal to 1 by t integration 0 to t qt dt. Or this Q will be equal to minus 1 by root 3 times only cos terms. What is first cos term? First cos term is this. This is the first cos term, VBIA cos of phi IA minus 120 degrees minus 5IB. This term will not be there, 2 omega t, this oscillating term, it will be gone. And then when you find average, then minus the second term. What is the second term? Minus VC IA times cos of phi IA plus 120 degrees minus 5VC. Then third term is this, plus VCIB times cos of phi IB plus 240 degrees minus 5VC. Then next is this, minus VAIB times cos of phi IB plus 120 degrees minus 5VA. And then next term is plus VAIC times cos of phi IC minus 120 degrees minus 5VA. And finally last term is this, minus VBIC times cos of phi IC minus 240 degrees minus 5VB. That's all. This is the average power, the average reactive power, which we got from that equation given by H. Akagi. So therefore, from here we can say that this reactive power, average reactive power, which is 1 by t integration 0 to t qt dt, unlike real power, like your real power was equal to PA bar plus PB bar, real power PA bar plus PB bar plus PC bar. And what was that equal to? That was VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C. You expect that our average reactive power should also give us similar term, like average reactive power should be equal to VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi C, but that is not true. So the average reactive power is not equal to this, VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi C. Average reactive power is this. You don't have these terms there, VAIA sin phi A, nowhere, plus VBIB sin phi B plus VCIC sin phi C. Whereas average real power is VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C. But average reactive power is minus 1 by root 3 times VBIA cos of phi IA minus 120 degrees minus 5VB minus VCIA times this plus VCIB cos times this minus VAIB times this plus VAIC times this minus VBIC times this. It is not VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi B. No, it is not that. It is because both voltages and currents have got unbalance. So let us take now second case, case 2, where only one quantity has unbalance. Let us assume only current is unbalanced. Let only one quantity, you can take voltages also, it's your choice. I have taken currents. Let only currents be unbalanced, whereas voltages are balanced. In the first case, we assume that both three-phase voltages as well as three-phase currents are unbalanced, and we ended up with a mathematical expression for instantaneous power, active power, and instantaneous reactive power. And we found that instantaneous active power is VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C plus oscillating terms PA oscillating plus PB oscillating plus PC oscillating. So it is not constant like a balanced three-phase system. Instantaneous active power is oscillating in nature. Whereas instantaneous reactive power, just few moments back you got an expression, and instantaneous this average reactive power is not VAIA sin phi A plus VAIB sin phi B plus VCIC sin phi C. It is a different equation which just few moments back we had derived, and I had put that here in this portion of the board. I had written that equation here. Now in the second case, case 2, let us assume that only currents are unbalanced, voltages are not. So therefore phase to neutral voltage, line to neutral voltage, or phase voltage VAT will be equal to root 2V sine omega t. VB will be equal to root 2V sine of omega t minus 120 degrees, fine, and VC will be equal to root 2V sine of omega t plus 120 degrees. So voltages are balanced. All the three voltages have same RMS value, V, V, V. So balanced three-phase voltages. But let us assume currents are unbalanced. So IAT, line current IAT, is equal to, let us suppose it is root 2 IA sine of omega t minus phi IA. Similarly, IBT, line current IBT, is equal to root 2 IB sine of omega t minus 120 degrees minus phi IB. And line current ICT is equal to root 2 IC sine of omega t plus 120 degrees minus phi IC. Here you can see currents are unbalanced because RMS value of line A current is IA, line B current is IB, line C current is IC, and they are not equal. IA not equal to IB, not equal to IC, not equal to I. Whereas here VA is equal to VB is equal to VC is equal to V. Voltages are balanced, but currents are not balanced. Now let us find the instantaneous reactive power. We will use the same equation for instantaneous reactive power in this case. So now I will write here instantaneous reactive power is given by instantaneous reactive power. It is given by Q of t is equal to minus 1 by root 3 times VBCIA plus VCAIB plus VABIC. So it is in terms of line voltages. Can we represent it in terms of phase voltages? Because what is given to us? We are given phase voltages, VA, VB, VC. We are not given line voltages. So we can represent this expression in terms of phase voltages. Let's call this equation as equation 1. For that, we may have to use the phasor diagram. For example, this is phasor VA, this is phasor VB, this is phasor VC, and if you find line voltage, this is phase voltage VA, phase voltage VB. What is this voltage? This is VA minus VB. This is phase voltage VAB. Line voltage VAB. Similarly, on this side, this is phase voltage phasor VA, this is VB, and this is VC. If this is plus VC, this is minus VC. And now you have this. What is this? This is VA minus VC. This is line voltage VAC. And similarly, if this is VA, this is VB, this will be minus VB. And draw the parallelogram. What is this? This is line voltage VAB. We have done it in one of the previous classes. Okay, this is line voltage VAC, this is line voltage VAB, and similarly if this is VA on this side, this will be minus VA, and you can now draw line voltage VAC, which is VA minus VC. उसके लिए आपको ये parallelogram complete करना पड़ेगा. It's this. So this is VAC. So we have three phase voltages, VA, VB, VC. And from phase voltages, we got three line voltages. VAB, line voltage, okay. VA. Where is VBC? VAB, VBC. VAB is this, VBC should be here. This is VBC. See, I repeat, this is the phase voltage VA phasor, this is VB phasor, this is VC phasor, 120 degrees mutually displaced with respect to each other. And now, how do you get VAB? VAB is VA minus VB. ये आपका VA है, ये plus VB है, ये minus VB है. Complete this parallelogram. This is line voltage VAB, which is the phasor sum of these two voltages, VA minus VB. Similarly, VBC. If this is VB, this is plus VC, this is minus VC. So VBC is VB minus VC. And VCA, this is not VAC, this is VCA. It is VC minus VA. So this is line voltage VAB, this is line voltage VBC, this is line voltage VCA. Now I want to represent line voltage in terms of these phase voltages, because we are given the phase voltages. We know VA, we know VB, we know VC. I don't know line voltages. What is VA? Just few moments back you have written, that's root 2V sine omega t. Similarly, this is root 2V sine omega t minus 120 degrees. This is root 2V sine of omega t plus 120 degrees. These are phase voltages. But in the equation we have line voltages. Can I represent these line voltages in terms of phase voltage? The answer is yes. Because what is line voltage? Line voltage is root 3 times phase voltage. Okay? So that means if I take VAB line voltage, you see this VAB line voltage is like this. See this VAB line voltage. This is your VAB line voltage. It lags behind phase voltage VC by 90 degrees. This is VAB, this is VC. So that means VAB line voltage can be represented in terms of phase voltage. It can be represented in terms of phase voltage. Which phase voltage? VC. So can I write like this? Instantaneous line voltage VAB is equal to root 3 times phase voltage VC at an angle of minus pi by 2. Line voltage is always equal to root 3 times phase voltage. Now this is your line voltage VAB and this is phase voltage VC. What is this angle? This is 90 degrees. If you are rotating in the counterclockwise direction, phase voltage VC leads line voltage VAB by 90 degrees, pi by 2. Or in other words, line voltage VAB lags behind phase voltage VC by pi by 2. So that's what I have written here. I have written line voltage VAB is root 3 times phase voltage VC. But what is the phase angle? VC leads VAB by pi by 2 or VAB lags behind VC by minus pi by 2. That's what I have written. So this is VAB. What about VBC? This is your VBC. Now this is your VBC and this is VA. Between VBC and VA also, the VBC is line voltage, VA is phase voltage. There is pi by 2. That means VA leads VBC by pi by 2 or VBC lags VA by pi by 2. So VBC I can write is root 3 times VA at an angle of minus pi by 2. Similarly, I can write line voltage VCA in terms of phase voltage. This is VCA, line voltage, and this is phase voltage VB. है ना, आपकी phase voltage VB है. In this case also, line voltage VCA lags behind phase voltage VB by 90 degrees. So line voltage VCA is equal to root 3 times phase voltage VB, but it lags behind phase voltage VB by 90 degrees. That's what I have written. So I can write these line voltages like this also. Line voltage VAB is equal to, you should see V is equal to V max sine omega t, isn't it? So V max, this is RMS value. So I have to write root 2, or if you multiply RMS value by root 2, if you are given RMS value, multiply that by root 2, you will get peak value. So root 2 into root 3 is already there, and this is RMS value VC sine of omega t minus pi by 2. This is VAB. So VAB is root 2 into root 3 times sine of omega t minus pi by, omega t, what is VC? VC is plus 120 degrees minus pi by 2. Because see, if you take VA as reference, VA is equal to Vm sine omega t. VB is equal to Vm sine omega t minus 120 degrees, and VC is equal to Vm sine omega t minus 240 degrees or plus 120 degrees. So VC with respect to VA is at an angle of plus 120 degrees. That's what I have written it. This is VAB. VBC, how can you write VBC? VBC is root 3 times VA, इसको root root 3, इसको root 2 से multiply कर लीजिए तो ये peak value बन जाएगा VA sine of omega t minus pi by 2. VA reference आप ले रहे हैं, so omega t minus pi by 2. And then VCA you can write as root 2 into root 3 VB sine of omega t. VB VA से कितना lag करती है? minus 120 degrees, and there is already this minus pi by 2. So these are the expressions for line voltages in terms of phase voltages. VAB is in terms of VC, VBC is in terms of VA, and VCA is in terms of VB. So substitute in this equation. So therefore, if I substitute in this equation, therefore instantaneous reactive power is equal to minus 1 by root 3 times what is inside VBC, and this is the expression for VBC. VBC is root 3 into root 2 VA sine of omega t minus pi by 2 into IA. IA is root 2 IA sine of omega t minus phi IA. ये हो गया this into this, right? Then plus VCA ये है आपकी. VCA is root 3 into root 2 VB sine of omega t minus 120 degrees minus pi by 2, nice, into IB. IB is root 2 IB sine of omega t minus 120 degrees minus phi IB plus VAB, तीसरी quantity. VAB is this plus root 3 into root 2, ये है VC sine of omega t plus 120 degrees minus pi by 2 into IC. इसको multiply करना है current IC से, whose instantaneous value is root 2 IC sine of omega t plus 120 degrees minus phi IC. That's it. अच्छा, यहाँ पे here I am writing VA, VB, VC, since we are assuming that there is unbalance in only currents. I is not equal to IB, not equal to IC, but voltages are balanced. VA is equal to VB is equal to VC is equal to V. So instead of writing VA, VB, VC, I will write V. So root 3, root 2 V sine of omega t minus pi by 2. Similarly here, root 3 into root 2 V sine of omega t minus 120 degrees minus pi by 2, and so on. So close this bracket. Let us expand it. So we can write QT is equal to, देखिए, if you take this root 3 out, root 3 is term में भी है, root 3 is term में भी है, root 3 is term में भी. So it will be root 3 by root 3. Root 3 by root 3 cancel हो जाएगा, so it will be minus times. Now what is inside? Root 2 into root 2 is 2. Okay, and v into ia, let me first of all write v into ia. Then root 2 into root 2 is 2. First term, sine of omega t minus pi by 2 into second term is this, sine multiplied by sine of omega t minus phi ia. ये तो हो गई पहली, प्लस v into ib, let me write v into ib, into root 2 into root 2 is 2 into this sine of omega t minus 120 degrees minus pi by 2 into sine of omega t minus 120 degrees minus phi ib. Okay, प्लस यहाँ से भी v into ic है, v into ic, then root 2 into root 2 is again 2 multiplied by first term which is sine of omega t plus 120 degrees minus pi by 2 into this term sine of omega t plus 120 degrees minus phi ic. That's it. Okay, now further simplification gives like this. If you further simplify this, your instantaneous reactive power for this case will be equal to minus times. Okay, VIA, so this is 2 sine A sine B, which is again equal to cos of A minus B minus cos of A plus B. So cos of A is omega t minus pi by 2 minus B, minus is omega t minus into minus plus phi ia minus cos of A plus B. A is again omega t minus pi by 2 plus B. B is omega t minus phi ia. ठीक है? So this is VIA into this. Then you have plus V into IB times 2 sine A sine B, which is cos of A minus B minus cos of A plus B. Cos of A is omega t minus 120 degrees minus pi by 2 minus B. B is omega t minus and minus plus 120 degrees plus phi IB minus cos of A plus B. Cos of A is again omega t minus 120 degrees minus pi by 2 plus B. B है आपका ये omega t minus 120 degrees minus phi IB. ठीक है? So this curly bracket closed plus this term plus V into IC into, this is again 2 sine A sine B, which is cos of A minus B minus cos of A plus B. Cos of A is omega t plus 120 degrees minus pi by 2, omega t plus 120 degrees minus pi by 2 minus B. B is omega t plus 120 degrees minus phi IC. So minus omega t minus 120 degrees plus phi IC minus cos of A plus B. A is again omega t plus 120 degrees minus pi by 2 plus B. B is omega t plus 120 degrees minus phi IC. That's it. Now further simplification will give Q of t is equal to minus times VIA. See, plus omega t minus omega t goes, so I get phi ia minus pi by 2. Cos of phi ia minus pi by 2 minus cos of omega t plus omega t is 2 omega t minus phi ia minus pi by 2. Okay, तो ये तो हो गई पहली टर्म प्लस V into IB times cos of, here also plus omega t minus omega t goes, plus 120 degrees minus 120 degree goes, so cos of phi IB minus pi by 2, phi IB minus pi by 2 minus cos of omega t plus omega t is 2 omega t minus 120 degrees minus 120 degrees is minus 240 degrees minus phi IB minus pi by 2. ये तो हो गई second term. Okay, then third term is plus V into IC times cos of, here again plus omega t minus omega t goes, plus 120 degrees minus 120 degrees goes, just phi IC minus pi by 2. Okay, minus cos of omega t plus omega t is 2 omega t plus 120 degrees plus 120 degrees is 240 degrees minus phi IC minus pi by 2. That's it. Okay, now we can rearrange the terms like this. We can write like this: instantaneous reactive power QT is equal to minus times VIA minus times VIA cos of, if I write pi by 2 first, this is pi by 2 minus phi IA, that doesn't make any difference, minus cos of, second term is minus cos of, इसमें भी पहले मैं pi by 2 लिखता हूँ, माइनस फिर लिखता हूँ minus times 2 omega t minus phi IA. Okay, if I take pi by 2 here, so I mean if I change the signs, minus pi by 2 plus pi by 2 बन जाएगा, plus 2 omega t minus 2 omega t बन जाएगा, और minus phi IA plus phi IA बनेगा. So I will take pi by 2 minus what is inside 2 omega t minus phi IA. Right? ये तो हो गया V in VIA times this thing plus VIB times cos of, this is pi by 2 minus phi, pi by 2 minus phi IB minus cos of, right? इसमें भी पहले मैं pi by 2 लिख रहा हूँ, pi by 2 cos of pi by 2 minus बाहर में निकालता हूँ, so what I get inside is 2 omega t plus 240 degrees, sorry, minus 240 degrees minus phi IB. Okay, पाई बाई 2 मैं यहाँ ला रहा हूँ और बाकी ये 3 टर्म्स में ब्रैकेट के अंदर लिख रहा हूँ. दैट्स ऑल आई हैव डन, नथिंग एल्स. प्लस V इंटू IC टाइम्स कॉस ऑफ पाई बाई 2 माइनस फाई IC, पाई बाई 2 माइनस फाई IC माइनस कॉस ऑफ पाई बाई 2 माइनस पाई बाई 2 मैं यहाँ ला रहा हूँ, व्हाट इज इनसाइड इज 2 ओमेगा t. ओके, माइनस 2 ओमेगा टी हो जाएगा ऑफ कोर्स, प्लस, हाँ माइनस तो बाहर ही मैंने निकाला, minus 240 degrees minus phi IC. That's all. So that comes out to be instantaneous reactive power, therefore can be written as minus times VIA. What is cos of pi by 2 minus phi IA? Cos of 90 degrees minus phi IA is sin phi IA. Sin phi IA. V into IA इसके साथ भी मल्टीप्लिकेशन में है, माइनस V into IA. Cos of pi by 2 minus this is sin of 2 omega t minus sin of 2 omega t minus phi IA, right? Plus V into IB. Cos of pi by 2 minus phi is sin, phi IB, sin phi IB, plus cos of pi by 2, this is sin of, minus sin of, what is inside 2 omega t minus 240 degrees minus phi IB, right? इसको भी multiply करना है V IB से, V into IB here, it's V into IB, just because this V into IB multiplies with this term as well as this term. plus V into IC times cos of pi by 2 minus phi IC is sin phi IC minus cos of pi by 2 minus this is sin of this, but V into IC is also there. Sin of 2 omega t minus 240 degrees minus phi IC. That's all. Okay. So therefore, what I can do, I can take these terms separate and these 2 omega terms I can take separate. 2 omega t means these are oscillations and this means this is the average value. So instantaneous reactive power will be therefore equal to minus times VIA sin phi A, VIA sin phi A, okay, plus VIB sin phi IA plus VIB sin phi IB, V into IB sin phi IB plus V into IC sin phi IC, V into IC sin phi IC. If I keep them in brackets, then minus times मेरे पास ये oscillation वाली terms बचती है, VIA, let it be curly bracket and this be square bracket, minus VIA sine of, what is this? What is the first term? 2 omega t minus phi IA. Yes, 2 omega t minus phi IA plus फिर ये वाली term VIB sine of 2 omega t minus 240 degrees minus phi IB plus तीसरी term ये VIC sine of 2 omega t minus 240 degrees minus phi IC. This bracket closed and curly bracket closed. That's all. This is the final expression, mathematical expression for instantaneous reactive power. Now, just like instantaneous real power for an unbalanced system when both voltages and currents were unbalanced, that is case A. Here you have constant terms VIA sin phi A plus VIB sin phi B plus VIC sin phi C, and you have oscillating terms. These terms are oscillating at 2 times the supply frequency, because here it is 2 omega, here also it is 2 omega, here also it is 2 omega. So that means if you find, अगर आप इसका average reactive power निकालेंगे, average reactive power will be equal to integration of this whole expression, 1 by t integration 0 to t qt dt. That is equal to ये 2 omega t वाली terms, oscillating terms सारी 0 हो जाएगी integration के बाद. So you will be left with only this minus times VIA sin phi IA plus VIB sin phi IB plus VIC sin phi IC. That's all. This is an interesting result. This means in a three-phase unbalanced system where only one quantity is unbalanced, either voltage or current. Here we have taken current as unbalanced, but you can take voltage also as unbalanced and current balanced. In this example, I have taken voltage as balanced and current as unbalanced. The average reactive power is not that previous equation which I had written previously for case 1. For this case 2, when only one quantity is unbalanced, the average reactive power is VIA sin phi A plus VIB sin phi IB plus VIC sin phi IC. But it does not mean that your average reactive power is constant like this. It has oscillating terms also, 2 omega t terms also. So it has oscillating terms also. And what are those oscillating terms? Let us represent those oscillating terms as QAT plus QBT plus QCT. And those oscillating terms are this. First is this VIA sine of 2 omega t minus phi IA plus VIB sine of 2 omega t minus 240 degrees minus phi IB plus VIC sine of 2 omega t minus 240 degrees minus 5 IC. Okay, so that's all. That's about a three-phase unbalanced system. Let us summarize what we have learned over last two lectures. Let me give you the summary of last two lectures. Summary is like this for a balanced three-phase system. Let us start with balanced three-phase system, which we have discussed in previous lectures. For a balanced three-phase system, the instantaneous active power, which is also equal to P three-phase power, that is constant. That is VI 3VI cos phi. Okay, and the instantaneous reactive power, when you used Akagi's research work and you got the equation for instantaneous reactive power, and if you remember that instantaneous reactive power was given by this expression minus 1 by root 3 VBC IA plus VCA IB plus VAB IC, and when we put VABC IA VCB VAB VBC VC and IA IB IC in that, we got the expression for instantaneous reactive power as Q three phase 3VI sin phi. That means instantaneous reactive power is also constant in a balanced. The instantaneous active power is constant. The instantaneous reactive power is also constant. That is for a balanced system. Then second finding is that for a three-phase unbalanced system, with both voltages and currents unbalanced, voltages and currents both are unbalanced. What did we find? The instantaneous active power is not constant. The instantaneous active power is not constant. It is not 3VI cos phi like a balanced system. What is it? The instantaneous active power, it has average value and it has oscillating value. The instantaneous active power is given by PA plus PB plus PC, that's the average terms, plus oscillating terms, PA oscillating plus PB oscillating plus PC oscillating. It's not constant like this. And if you find average power, average active power, P three phase, that was given by PA bar plus PB bar plus PC bar. I'm talking about average. That was equal to VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C. Average power. Okay. That means, and what was the average reactive power? Average reactive power Q three phase, that was not equal to VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi C. That was not equal to this. That was equal to something else. That relation just few moments back I have given you. I have derived that relation. Okay. Now this is for a three-phase unbalanced system where both quantities, voltages and as well as currents, are unbalanced. The instantaneous active power is having oscillating components. Instantaneous reactive power is also having oscillating component. And average active power is VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C. But average reactive power is not equal to VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi C. It is other than this. Okay. And then third point is for an unbalanced three-phase system, with only one quantity, either voltage or current as unbalanced. As far as your instantaneous active power is concerned, that remains same. That does not change. PA bar plus PB bar plus PC bar plus oscillating terms. PA oscillating term, oscillating component plus oscillating component PB plus oscillating component PC. And average active power. I should write that like this in short. Average active power is this. PA bar plus PB bar plus PC bar, that is equal to VIA cos phi A plus, if you consider voltages balanced and currents unbalanced, VIB cos phi B plus VIC cos phi C. Same equation as we get for case 1 when both voltages as well as currents are unbalanced. Same, active power does not change. Active power is oscillating. It has constant term, average term as well as oscillating term. And average active power is this, VIA cos phi IA plus VIB cos phi IB plus VIC cos phi IC. But what about reactive power? Your instantaneous reactive power is given by, what is the instantaneous reactive power given by? Just few moments back we found that that is equal to minus times VIA sin phi IA plus VIB sin phi IB plus VIC sin phi IC plus oscillating terms, say QA oscillating plus QB oscillating plus QC oscillating. I am not writing the, just few moments back we have derived those oscillating terms. Then therefore what is the average reactive power? Average reactive power Q, capital Q, 3-phase, that is equal to VIA sin phi IA plus VIB sin phi IB plus VIC sin phi IC. That's important. Whereas in first case, when both voltages as well as currents were unbalanced, this average reactive power was not equal to, here I have written here, not equal to VIA sin phi A plus VBIB sin phi B plus VCIC sin phi C. But in case unbalance is only in one quantity, either voltage or current, not both, then average reactive power is VIA sin phi IA plus VIB sin phi IB plus VIC sin phi IC. Of course, this is the average reactive power. The instantaneous reactive power is this average term plus it has oscillating components also. And last observation is, which we have not made in these equations, which you can make only if you solve a numerical example, that in 3-phase unbalanced systems. This is another finding. The line losses in 3-phase unbalanced systems, the line losses are higher as compared to 3-phase balanced systems. None of the equations which we have derived today or in the previous lecture, they support this statement. This statement you can prove only when you take a numerical problem, solve that, take first the balanced system, find the line losses, and then make that system unbalanced, either both currents and voltages unbalanced or one quantity unbalanced, and find the line losses again. You will find that in a 3-phase unbalanced system, the line losses are higher than those in a balanced 3-phase system. So these are 4 very important findings. I repeat, the first finding is that for a balanced 3-phase system, the instantaneous active power as well as instantaneous reactive power are constant. The instantaneous active power is 3VI cos phi, instantaneous reactive power is 3VI sin phi. So therefore, when instantaneous active power is constant, 3-phase motors which are fed from 3-phase balanced supply, they don't develop any torque pulsations, any oscillations, any vibrations. They run smoothly. But as soon as there is unbalance in the system, say for example we have a 3-phase unbalanced system with both voltages and currents unbalanced, the instantaneous active power is not constant. It has a constant average term and it has oscillating term, which I have already written here. And therefore it loses the advantage of a balanced system that power is constant. So therefore when a three-phase AC motor is fed from a three-phase unbalanced system, three-phase unbalanced voltage supply, so the torque has pulsations, the torque has ripples, the motor runs with vibrations because instantaneous power is not constant. Okay, and then average power is VAIA cos phi A plus VBIB cos phi B plus VCIC cos phi C. And reactive power, instantaneous reactive power has constant, instantaneous reactive power is also oscillating, and it is not equal to VAIA sin phi A plus VBIB sin phi B plus VCIC sin phi C. And then we have also observed that if there is unbalance in only one quantity, either voltage or current, then instantaneous active power is again oscillating, and same equation VIA cos phi A plus VIB cos phi IB plus VIC cos phi IC. But instantaneous reactive power, is given by this equation. It has average DC, constant values and oscillating values. And average reactive power is VIA sin phi A plus VIB sin phi IB plus VIC sin phi IC. And finally, three-phase unbalanced systems give higher line losses than three-phase balanced system. So with this, I will end my today's lecture. So I hope that you will, I advise all of you that you revise last two lectures, this lecture and previous lecture, which are focused around discussing three-phase unbalanced systems. Both cases, case 1 when both voltages and currents are unbalanced, and case 2 when only current or voltage is unbalanced. Analyze for yourself, derive the equations yourself, and write the summary. Try to understand the summary of these lectures. Try to understand what happens when the system becomes unbalanced. Okay. With this, I will end my today's lecture. Inshallah, in our next lecture, we will take third case, that is three-phase balanced supply with harmonics. I wish all the best to all of you. Thank you.